Hello. In today's video, we're going to talk about what are our goals in applying functional programming to the game development. And we have to talk about that because in itself, functional programming isn't a goal, it is a technique and it is a tool. And we have to have many of those tools to know which tools should be used in which situations and to achieve our goals. And the goals are: we want our programs to be stable at runtime. We want them to have runtime stability. Things should not crash. Basically, your program, if you run it, it should work. We want to have compile time correctness. So we want errors to be caught in compile time ideally, and if your code compiles, it should work, and it should work correctly without any glitches or incorrect results. We want the code to be understandable. It should be easy to read and easy to understand for everyone, no matter how much experience they have, whether they have been with the project for a year or 2 years or 5 years. We want the code to be maintainable. We want so that down the line, when we change the code, things should not break. And we want the code to be testable and be testable easily, so the tests would actually be written and they wouldn't be brittle, requiring updates at any slight change. Let's talk about runtime stability first. Why do runtime errors happen? And runtime errors are essentially, failures in the programmer's code. And these errors happen when you assume that the state of something will be X, like, I don't know, a socket will be open for writing, or a collection will be non-empty, or even a reference will be not null. And it just isn't so in the actual runtime. And in theory, runtime errors are completely avoidable. If there was no way to abort the program by throwing an exception or killing the process, you would be forced to handle everything. Like if there's no escape latch in the middle of the program, you have to handle things. However, in practice, it is often more practical to kind of assume that the situation is exceptional and then throw an exception or just exit the program instead of handling things. For things like, this should never happen, or things that you cannot prove statically in the code, but you know that are handled in runtime. So really the problems start when ordinary situations, like, I don't know, you're trying to open the file and this might fail because the file might be locked or it might not exist, etc., are being treated as an exceptional situations. And functional programming helps us with runtime stability with a couple of ways. So first, functions can return errors as values, and instead of having this implicit failures, whereas you don't really know how can a function fail, you can see with functional programming, you can see from the type signature how it can fail. You can see that it's gonna either return an IO error here, or the contents of the file instead of just opening a file. Then we can lean on the libraries and we can use the functional combinators to make handling these errors very easy. So for example, if you have a bunch of paths and you want to read all of the contents from these paths, you can just apply this read file function here and you can say validate all, and then you will get either an error list or the results. So it's very easy. And if you take a look at the language like Go, they kind of do this. They don't have exceptions, so they rely on these explicit error values, but they also do not provide any libraries to handle this. So your code is just basically pepper sprayed with, if error, then do this, instead of proper handling techniques. In functional programming, we can also make illegal states irrepresentable. So you can have a runtime error if it's impossible to construct a data structure which represents the illegal state. So one of my big questions of for C# is, why do array lengths and collection lengths return integers instead of unsigned integers? Like, the language supports unsigned integers, and in a length of a collection will never be negative. So why does it return something that can be negative? And then you have to validate that in all of the places, and or more likely what happens is everybody kind of ignores the negative side of these integers and just assume that it's just fine. But if you define, that, hey, there's a length method here and it returns an unsigned integer, then you don't have to worry about that anymore, and there's no capability to even have a runtime error. Compile time correctness. So we can't really avoid all of the logic errors in our code. Unfortunately, we are still humans writing this code, but we can avoid some of them by, for example, using a good type signature. So if you have a list and you have a function that returns a random element, instead of just saying, oh, I'm just gonna give you something, you can explicitly say that I might not give you anything because the list might be empty. And then when you use this, there's always a chance that you will forget about this scenario where the list is empty. While you use this, you will always be forced to handle this explicitly and will be reminded. You can still handle it by throwing an exception here and saying this should never be done, but at least it is now your choice, your deliberate choice, instead of you forgetting that lists can be empty. We can constrain our types to enforce invariance. Basically, we can say, for example, here we have this class asset GUID, and it has a private constructor and it has the public create method. And essentially, if you have an instance of this type, that means at least we have validated with the Unity asset database that this ID, this string, is actually an ID pointing to a valid asset at the time of creation of this thing, instead of just some random string. We can use techniques like proof values to enforce ordering. So if you have two side effectful functions, like, for example, replenish hit points and apply attack damages, and you need to enforce order between them, what you can do is you can just define a struct which has no data in it, but this thing will return the proof value, and then we will require that proof value as a parameter here. So what this does is essentially it enforces the order of these functions. You cannot call this without calling this first, because you will not have the proof. So it enforces the order in the compile time instead of relying on programmer not making a mistake. And there's other techniques that we will be covering in this course. At the end of the day, our goal is simple. Get out of this dreaded write code, compile it, run it, then crash, have some errors, debug those errors and fix it, and then go back to the beginning of the cycle and just replace it with this simpler write, compile, run cycle where after you compile things, if they compile, they just work. Understandability and maintainability. So code is written once, but is read many times, and often a lot later. It might be a couple of days, it might be a couple of months, or a couple of years later. But we need to make sure that anyone, after any amount of time, would be able to read the code and understand its intentions, and be able to modify it without introducing issues into the code, without it causing any regressions. And ideally, that should be done without an extensive research first. So again, in theory, you could, when you need to modify existing code, in theory, if you study it long enough, you should be able to figure everything out. But in reality, it's often just not very practical. You can't say, I'm going to study this code for 2 months and then I'm going to add this new feature into it. So what people do is they just look around and then they assume things. So we want to get rid of that. We want to help people understand things quickly. And to do that, we will cover things like semantic types, what is a good and bad function type signature, code comments, where should we write them, what should we write in them, and when should we write these comments, type-driven system design, and the static traceability of the code, how find usages in your IDE is your friend, and why you should avoid leaning on runtime things and runtime reflection. And for the testability goal, essentially, what are tests important for? Tests are important for when we initially write code, for making sure we implemented the right thing, and then later down the line, making sure that the implementation will not break when we then refactor things and change the code down the line. And again, in functional programming, pure functions help us because they are ultimately testable. So if you have this calculate level up time here, which relies on a side effect of getting the current date, it is hard to test this. Well, you have to rely on the side effect as well. Whereas if you turn that into a pure function here, now it's very easy to test. You just give 2 parameters here and then you get back another parameter. So what are our next steps? Next, we will start looking into the basic building blocks of functional programming. And for that, I'll see you in the next video. Bye.